I would like to welcome each one of you for the ENR 5261 Environmental Soil Physics class. As the weather created some situation that we could not meet in person, you received my email. I appreciate your understanding. Therefore, we are recording the lecture 1 for you to see it at your leisure whenever your time permits, and we'll meet in person on Wednesday this week for the same class and probably discuss additional points that you may have. I'm going to use a lot of Greek alphabet, so we will have a slide, and these slides, by the way, are available to you as well, and we'll provide you a link to get these slides. So Greek alphabet, which I'll use quite often in this class. I will also use certain numerical prefix, such as from 10 to the minus 18 to the 10 to the 18, especially in relation to the climate and carbon stock and water stock and so forth. So I expect you will be familiar with these prefixes like exa 10 to the 18, beta 10 to the 15, tera 10 to the 12, giga 10 to the 9. Mega is very common. Mega is metric ton. That's 1,000 kilogram, of course. And then kilo 10 to the 3, deca, hecto 10 to the 2. Hectare is common term we use. And centimilli, micro, nano. We use up to nano quite a lot. So be familiar with these symbols and prefix of the numerical figures that we will use in this class. We will also use some algebraic functions to develop equations. For example, what's a linear function, which most of you are familiar from your high school algebra, y equal to ax plus b, where a is the prefix of the number and the b is the constant. Logarithmic, which is a natural log. Power function, y equal to 8mx to the b. Exponential function, and polynomial. Linear are the most common that we will use in this equation. We will try to minimize use of these calculus equations. Mostly will transform into algebraic, but wherever possible, we'll explain what those are. So begin with, let's define what the pedosphere is. Pedosphere is a three-dimensional representation of soil with a plant growing in it. And therefore, a plant has its root system in the soil. Plant has evapotranspiration, that the water lost from the leaves. It has soil evaporation, the water being lost from the soil surface. And of course, there are many components like photosynthesis, the rate at which the plant grows, evapotranspiration, evaporation, precipitation. These terms are used in the hydrologic cycle. And of course, we have weathering, which leads to the formation of new soil, and leaching of the nutrients, especially the elements and other material that we add into the soil, like fertilizer, herbicide, pesticide, which are leached into the groundwater. And this is a pedospheric representation and the dynamic action that happen of soil with the environment. That deposition, that means material brought into by hydric or aeolian, water or wind processes, and the erosion, of course, that takes the material away from the soil. So deposition and erosion. And then within the soil profile, there are several translocation and transformations which take place, and we will talk about some of them as far as the physical processes are concerned. We are limiting this class to physical and hydrologic and mechanical processes, not chemical or biochemical. That brings us to the definition of soil. It's a four-dimensional body: length, width, depth, and time. Time is the fourth dimension. Soil changes with time. Soil changes with length, width, and depth. Therefore, it's a four-dimensional body. And it is at the interface of atmosphere, lithosphere. Atmosphere, as you know, air, lithosphere, the bedrock. Interface of that is the soil. and it's in dynamic equilibrium with the environment. And it's a source of many, many ecosystem services. That dynamic equilibrium is important because soil changes over time because of anthropogenic and natural disturbances. So what is then the soil physics? It's a study of soil physical properties and processes. There's a difference between property and process. Bulk density is a property of the soil. Color is a property of the soil. Water content is a property of the soil. Process is mechanism that change these properties. And it includes the soil physical, includes the prediction of natural managed ecosystem in relation to soil functions of value to human and nature. Nature is more important. Human are part of nature. So as long as we can understand the value to the nature, the human part is automatically built into it. And it's a science of soil physics that deals with the forms, interrelation, and changes in 4 components and 3 phases. And we should understand what are the components and what are the phases. And I'll come back to that in the next slide. Then there's a term called physical edaphology. Pedology is basic soil science. Edaphology is a study of soil in relation to plant. When the plant comes into the picture, how soil affects plant and how plant affects soil, it becomes edaphology. So edaphology is a science dealing with application of soil physics to agricultural land use. The study of this physical phenomena of soil in relation to climate, plant growth, soil properties, and anthropogenic activity is also called physical edaphology. So edaphology is the proper term. And what's then the environmental soil physics, which is the title of this class? It's a study of soil properties and processes in relation to environmental factors such as climate, gaseous emission, water quality, non-point source pollution, soil degradation, human health. Human health, how soil affects human health and vice versa. And many other ecosystem services which are affected by soil physical processes and properties. These are the 3 components, the solid, and solid has 2 types, organic and inorganic. That's where it becomes the 4 components and the 3 phases. The phases are solid, liquid, and gases. Components are organic solid, inorganic solid, liquid, and gases. And that's the difference. Under optimal condition, the solid phase comprises about 50% of the total volume, and liquid and gas is the remaining. And ideally, there should be about 25% each. But it's very rare that they are 25% each. When soil is saturated completely, the gaseous phase is 0. And when soil is completely dry, the liquid phase is 0. So, and it varies with time. The volume of liquid increase at the expense of the gas and vice versa. So as the liquid increases, gas decreases. As gas decreases, liquid increases. But at the same time, when soil bulk density goes up, the solid component in volume also decrease. That's why the reason for the increase in bulk density. So soil physics then, in relation to environment quality, we look at the greenhouse effect, that the gaseous emission from soil, CO2, CH4, NOx. NOx is the many NO, NO, N2O, NO2, NO3, so forth. Carbon sequestration through aggregation of soil, and the global carbon cycle. Then we look at the acid rain, like water quality, vegetation cover, biodiversity. We study fresh water resources and quality, suspended solid, dissolved material in it, pathogens, and how those affect soil and any other living organisms above and below the soil. And of course, we look at the particulate matter in air, such as happened by wind erosion and blowing salt. And there are interaction amongst them. There's nothing by itself. They all interact. And this is the class soil environmental physics class, environmental soil physics. Climate change, water quality, hydrology, the properties of the water, properties of the solid substances, and air quality, air diffusion in relation to climate change. That brings us to the looking at the soil-water interaction and air. The voids, the pore space, contain water and air. And if the soil is saturated, as in the central circle, there is no air. And as soil is completely dry, there's no water. Normally, we have soil with some water and some air. That's called moist soil. So A is a moist soil, B is a completely saturated soil with water. That means all pores are full of water. And then where the soil is completely dry, it has only air in it and no water. So we have moist soil, water saturated soil, and completely dry soil. And we will study dynamic of soil in relation to moist, water, and air in soil at different levels. We have a dense soil and a loose soil. A loose soil is porous soil. A loose soil has more pore. And when soil is compacted, such as by heavy weight passing on it, like a weight of a tractor, the porosity decreases. The air is squeezed out. Therefore, relative proportion of solid is more than that of voids or pores in it. So we have a dense soil on the left and we have a porous soil on the right. Ideally, as we saw in previous slide, there should be 50% solid and 50% voids. And of the 50% voids, 25% should be water and 25% air. That's the ideal situation. What are some of the dominant soil physical properties and processes? For example, we have a compaction is a process. Soil bulk density is a property. If the bulk density goes up, soil is being compacted. If bulk density goes down, soil is being loosened. Its bulk density is decreasing. Similarly, other properties that affect compaction are particle size and soil structure. And we'll talk about these properties in more detail one by one. We have soil erosion, a process. Erodibility is a property. Erodibility indicates the ease of the system of soil by which can be transported by water and wind. That's erodibility. Soil structure is the formation of aggregation of the soil. Hydraulic conductor is the ability of the soil to transmit water. Infiltration rate is when the water passes from air-soil interface into the soil. And then we have a transportability of the soil in terms of sediment being transported by water in runoff, or sediment being blown away by wind in wind erosion. So this is erosion and the property that affected. Water movement is a process. Porosity is a property. Hydraulic conductivity is a property. Potential gradient, we will talk about it when we talk about soil water. And tortuosity, the pathway, how long the actual path is vis-a-vis the direct distance between the two points, that's the tortuosity. Aeration is a process. Porosity, pore size distribution, concentration, gradient of air, diffusion coefficient are properties. So there are properties which impact processes. Sedimentation is a process. Particle size distribution is a property. Heavier particles sedimentation happen quicker. Particle density is a property. Dispersibility, how soil disperses when it is in water or air. Those are properties. And subsidence is a process. And soil strength, soil water content, trafficability of the soil are properties. Absorption, desorption are processes. Surface area and charge density, electric charge density on the particle are properties. Diffusion is a process, concentration gradient of diffusing substances, oxygen, water, nutrient are properties. Tortuosity, Porosity, total pore space, pore size distribution are properties which affect diffusion. Gaseous emission, emission of CO2, emission of CH4, emission of N2O, which affect global warming, leaching of nitrate are properties affected by porosity and moisture content, Fs of T and theta, and all these affect gaseous diffusion, which change because of change in composition of soil and air in the atmosphere. Soil air is different than air in the atmosphere. That's why gases from soil diffuse into the atmosphere. And then we have non-point source pollution. Pollution which is diffused over the entire landscape, coming from the entire landscape. So pollution from agriculture is called non-point source. Vis-a-vis, for example, pollution from an industry, a factory, which is a point source. And this is affected by properties such as erodibility, water infiltration rate, crust, and moisture content. So those are the difference between properties and processes. I'm going over quickly because we'll be discussing each one of them in detail in separate lecture. Then there are different properties of phases and components. For example, solid phase has two components, inorganic and inorganic. Inorganic components are minerals such as feldspar, magnetite, garnet, hornblende, silicates, or secondary mineral. And these properties affect the bulk density, which is symbol rho, of the density of the material. Then the organic components are remains of plants and animals at different stages of decomposition. In most soil, that's less than 5%. And they affect the large areas, surface areas large. They affect the electrical properties of the soil. They affect the gaseous composition of the soil. And the density of the organic material compared to the inorganic is much less, 0.6 to 0.8 megagram per cubic meter. Sometimes you may see density as a gram per cubic centimeter. So 0.6 to 0.8, which is about 1/3 of what is the density of the material, which is inorganic, ranging from 2 to 2.8 megagram per cubic meter. Gram per cubic centimeter, the same thing as megagram per cubic meter. So numerically, 1 gram per cubic centimeter, such as the density of water, is the same thing as 1 metric ton per cubic meter. So 1 cubic meter of water weighs 1 metric ton, or 1 cubic centimeter of water weighs 1 gram. Therefore, gram per cubic centimeter numerically is equal to megagram per cubic meter. Then the liquid phase, which is a salt solution, which is aqueous solution of many ions in the solution of soil, such as sodium, potassium, calcium, magnesium, chlorine, nitrate, phosphate, sulfate. And these are heterogeneous substances in terms of property. They're dynamic. They keep changing over time. And the density of water, as I just explained a moment ago, is 1 gram per cubic centimeter or 1 megagram per cubic meter. Remember, 1 megagram contains million gram. 1 cubic meter contains 1 million cubic centimeter. That's why they are the same. Then the air in soil, which is the gaseous phase, and the air of different types, in addition to nitrogen and oxygen and CO2, which are mostly in the atmosphere. Soil also have a high concentration of C2H6, H2S, N2O, and NO and other substances. And the density of gaseous material varies from about 1 to 1.5 kilogram per cubic meter. See, the air has a density of 1 kilogram per cubic meter, while water had a density of 1 megagram per cubic meter. See the difference between the two? They differ by a factor of 1,000. Therefore, soil physics is a science of the study of phases and components, their interactions with one another, and with plant growth and environment in relation to perturbation, either natural or human. And that is what we will discuss in this class for the next semester, for the coming semester. Finally, I want to leave with you today a series of equations which relate the components solid, water, phases solid, water, and liquid are four components, three phases and four components, because solid phase has two components. So we have fluid, we have solid, and the fluid are two parts, gases and the liquid. Therefore, we have three components and we have four phases because solid is organic and inorganic. And that is why we have four phases. And how do we relate them? For each phase, we have volume. For example, volume of gases, volume of liquid, which is the volume of fluid together. We have volume of organic material, and we have volume of solid or the inorganic material. And together these volumes, if you combine all solid and fluid together, we get the total volume. So volume of gas plus volume of liquid plus volume of organic plus volume of inorganic, or volume of fluid plus volume of solid gives us the total volume. Corresponding with each volume, then we have the mass, like mass of gas, mass of liquid, which is the mass of the fluid together, mass of organic material, and in terms of mass of inorganic, and that is mass of solid. And we combine mass of solid and mass of fluid together, and we get the total mass. So a schematic which shows the mass of volume of different components and phases and how they change by management, by human activities, and by natural processes. Studying this volume and their change and their dynamic is what solves physics. Therefore, understanding some of those basic relations, which is 10 different equations, which I'll give you in a moment, I would urge each one of you to study them at home. Today is a good time. You probably don't want to go out in a snowing weather. So look at these equations. Like what's particle density? Symbol rho of S. An equation is mass of solid by volume of solid. And the units are either gram per cubic centimeter or megagram per cubic meter. That's a particle density. Mass of solid by volume of solid. If you change the volume of solid to total volume, V of T as in equation 2, then it becomes a bulk density. So mass of solid by total volume, the same units, megagram per cubic meter or gram per cubic centimeter, is the bulk density. So the difference between particle density and bulk density, mass of solid is the same, the denominator changes from volume of solid to total volume. And that's the bulk density. Then we have bulk density when you add in the mass of solid, also mass of water. So mass of solid plus mass of water divided by the total volume is wet bulk density. Now these three relations are very critical to understand, because in most time we see how the bulk density changes. Particle density does not change. It's constant. Bulk density changes by plowing or trafficking or snow or wetting or drying. Traffic, any cultural practice. Wet bulk density changes whether soil is wet or dry. After rain, soil is saturated, wet bulk density is much higher. When soil is completely dry, it's low, and it changes every minute because water evaporation is happening. Then we have a total porosity, F of T, which is volume of water over total volume. Volume of voids, not water, volume of voids. VV is voids. That means the fluid. That's the volume of gas plus volume of water. So volume of gas plus volume of water, which is volume of voids, divided by total volume is the total porosity. And then we have a fifth equation, which is called void ratio. It's symbol E. And it's volume of voids that's the gas plus water, over total or volume of the solid component. So the difference between porosity and void ratio is the denominator is volume total, V of T, and in void ratio is solid. Therefore, volume of solid is much less than the volume total. Therefore, in general, E is much lower in terms of if the V sub t is higher, the F sub t value is higher than the E value because the V sub t denominator is larger than V sub S, which is smaller. So understand the difference. Like here we were dividing by the V sub t and V sub S. Here we are dividing also by V sub t, but here we had a mass, here we have volume of voids and solids. Then we have one very common property and very first lab on Thursday, you will see it. We will also monitor bulk density on Thursday, but we'll also monitor the water content on Thursday. And water content is two types: gravimetric, that's a mass of water by mass of solid, and volumetric water content, which is a volume of water by total volume. So these two equations are also very practical important, and you will determine them on this Thursday. Then we have a saturation percentage. That's the volume of water divided by volume of voids multiplied by 100, volume of water divided by volume of water times 100. And we have liquid ratio, which is symbol theta of L, which is volume of water by volume of solid. Volume of water by liquid ratio. Then we have aeration porosity, which is F sub A symbol, the volume of air divided by total volume. So colleagues, students of 5261, these 10 equations are this most basic thing which will be repeated in one form or the other in each of the subsequent lectures of this class of soil physics. And your first practical on Thursday will be based on measurement of some of these parameters. I would strongly urge you to take your time and read and understand these equations. You do not have to memorize them. You should have handy notes somewhere and understand how they are calculated, how do they change by management and by natural processes, and what their optimum value is for crop growth and for other uses of soil. And we will consider other uses of soil engineering, construction, dam, building, foundation, and so forth. And these are those properties which are very critical. So please repeat and study again until you understand these 10 basic properties. I'm going to give you some example, at least one example. And let's say a soil, and you will be doing this in your lab on Thursday. So we have a core of soil, and we will see that core. It's a cylinder, which diameter is 7.6 centimeter, which is approximately 3 inches if you want to talk about. By the way, inch and pounds and feet and yard are not used in this class. We only use metric units: millimeter, centimeter, kilometer, meter, gram, microgram, nanogram, kilogram, megagram, gigagram, teragram. No pound, no foot, no yard, no, that's not. So a core of soil is a 7.6 centimeter in diameter, and it's 7.6 centimeter deep. And this core weighs 300 grams when it's empty. And the total core plus soil, wet soil, weighs 1,000 grams. And then you dry this core at 105 degrees centigrade, as you will do with your sample in the lab, and the core weighs 860 grams. So we want you to calculate several properties. So going back to those equations then, total volume of the core, pi r square h, pi is 3.14, r is 7.6 divided by 2, 3.8. You square it, centimeter square. By the way, do not forget the unit. See, if I have pi, it had no unit, 3.8 centimeter, you put it and square it and put 7.6 is the height and put centimeter. So don't forget the unit. So 3.14 times 3.8 times 7.6, you multiply it, you get 345, and centimeter square and centimeter you multiply, you get cubic centimeter. If you forget the units, you have only 345 and you do not know what it is. Therefore, units should never be forgotten. Never leave them out. So core weight was 300 gram. So weight of then the wet soil or weight of the soil which we have is 100,000 total weight minus 300 gram with the weight of the core is 700 gram. So wet soil then weighs 700 gram in its total volume of 345 cubic centimeter. So then the weight of the dry soil will be 860 minus 300, that's 560 gram. By the way, you'll be doing this measurement in your first lab practical this Thursday. So please understand these and study tomorrow or today, whenever you find time. So then wet bulk density, the total mass, m's of T, divided by total volume, V's of T. So 700 gram wet soil weight divided by 345 cubic centimeter. And remember the units, gram and cubic centimeter, and the numerical values 700 and 345. Divide that and you got 2.03 gram per cubic centimeter. So keep the units together. Do not leave the units out. Otherwise, you would not know what you got. Then you calculate the dry density, which is 560 gram divided by 345. You got 1.62 gram per cubic centimeter, which is the same thing as a megagram per cubic meter, because the total number, million gram in a megagram and million cubic centimeter, 1 cubic meter. So the units gram per cubic centimeter is same thing as a megagram per cubic meter. Then we calculate gravimetric moisture content, mass of water over mass of solid. So that is 1000 gram minus 60 gram divided by mass of solid 560. And you get 140 gram divided by 560 gram. Gram and gram will cancel and you will get a dimensionless unit. So this is very simple example and your textbook. And you, by the way, don't need to buy the textbook. There's one copy available in the library, close reserve. And you can read that. And there is one which I can also give you online electronic version link to the book that you can have. On Wednesday, I'll share it with you. Let's do one more example. We have 1 liter of dry soil sampled from a farm which requires 300 grams of water to completely saturate it. So 1 liter of dry soil sampled from a farm requires 300 grams of water to completely saturate it. And from this information, calculate his porosity, volume of water required to saturate the plow layer, which is 20 centimeter deep, of 1 hectare of farmland. So that's the question we have. So solution, what the porosity? Porosity is volume of water over total volume. Therefore, 300 gram and 1 liter, 300 cubic centimeter of water is the same as gram of water, by the way, because the density of water is 1. So in terms of volume, 300 cubic centimeter over 1000 cubic centimeter is 0.3 cubic meter per cubic meter. Now, some people say porosity is 0.3. That is correct numerically, but not exactly because the units are not there. So it's 0.3 cubic meter per cubic meter. That's correct, complete answer. Then if you want to calculate how much depth of water is required, it is a depth is porosity time depth. Therefore, 0.3 is, by the way, here is a technical mistake in this equation. It should be the whatever the total water content is, which is volume of water or total volume. So that is what it should be. Water filled pore. That will be another way to say that. So it's not total porosity. It is volumetric water content, 0.3. And maybe Maggie will remind me to correct this equation. So this is 0.3 multiplied by depth of water, that is 6 centimeter water. 6 centimeter of water per hectare is required. So 6 centimeter of water per hectare, total volume of water per hectare, that's 6 times 10 to the 5 liter. That's the water to be added to reach that volume if you are irrigating the soil. If you are draining the soil, then that means this is the amount of water that will be coming out of the soil to be stored into drainage pipe. So that was example 2. Let's see if we can do example 3. Calculate particle density. Rhos of S is particle density. Rhos of B is bulk density of a mixture containing 48% by weight of quartz, 50% of vermiculite, that's clay, quartz is sand, and 2% by weight of soil organic matter content. So you want to calculate. So what is the solution? From table 2.1 in your book, you will see that the particle density of solid is 2.65 megagram per cubic meter. Particle density of quartz is 2.3 of vermiculite and 1.4 of soil organic matter content. Therefore, if you put in the equation 1 upon bulk particle density, 0.48, 48 by 100 is 0.48, divided by its particle density 2.65. Then 50% is 0.5 divided by its density 2.3, and then 0.2% is 0.02, 2 by 100 is 0.02, divided by its density, which is 1.4. And you add up all those density 0.142, and if you take reverse of that, then you get the particle density of the soil 2.43 gram per cubic centimeter or megagram per cubic meter. I think those are the 3 examples that I had. And then there are some other basic equations that are very handy for you to keep notes. You can write these 3 equations on a piece of paper. So many times people ask you questions. One of the equations is what is total porosity equal to? How do you calculate it? So total porosity F sub T is 1 minus rhos of B is bulk density divided by rhos of S, which is particle density. And when you take the difference between that, you get saturation percentage. Theta says total porosity, the same thing as moisture content of the soil when it is saturated, completely saturated. All pores are full of water, no air. So total porosity is 1 minus bulk density or particle density. It's also equal to total water content when all pores are full of water or saturated porosity. We calculate volumetric water content from gravimetric water content, that is mass of water or mass of solid, time the rhos of B or rhos of W. That's a ratio of soil density to ratio of density of water, which, by the way, from your physics is specific gravity of soil. So ratio of the bulk density of soil to bulk density of water is specific gravity of soil. And this could also mean rhos of wet bulk density minus dry density divided by the density of water. And the density of water is 1 for practical purposes. Density of water is 1. 1 what? 1 gram per cubic centimeter or 1 megagram per cubic meter. So that's the second equation, which is very, very good to keep handy. And third is how to calculate air porosity, F sub A. So difference between total porosity, F sub T, F sub A, how many pores are full of air. So that's the difference between total porosity minus the water content. And water content volumetric is theta. So that's F sub T minus theta. That's the aeration porosity. And fourth equation is gravimetric water content. And gravimetric water content is wet density minus dry density divided by dry density. That's another equation which is very handy And finally, depth of water in a soil. And that is volumetric water content and the depth of the soil itself. Volumetric water content as a ratio and depth of the soil in centimeter. It gives you equivalent depth of water in the soil. So this is kind of a very quick summary of the introduction of 10 basic mass volume relationship, of which I've given you 5 equations in the last slide, which are very, very commonly used almost in most of the lecture that we'll be talking for the rest of the solid physics class. So I recommend that you get this lecture online. I'm going to request Miss Maggie Willis to put it online for you to receive this email, the lecture recorded, as well as the actual, so that you can repeat yourself and study more. And if you get a copy of the book from the library or go to the library and read it, you will see that this is chapter 1 summary. With that, I again once regret the inconvenience that happened because of the natural factor, but the recorded lecture is available to you. And I personally look forward to welcoming you to the class on Wednesday. Have a very good day. Thank you for having this class, and we look forward to working with you for the rest of the semester.